Now, how are we gonna deal with this? Okay, now first sight, we might be very tempted to kind of put inside the hyperbolic cosine. Okay, hyperbolic cosine is half of e to the x plus e to the minus x. Now we see that the arguments here are the same, but it's, it just differs by a minus sign. So we can kind of fit the hyperbolic cosine inside, but we cannot, because the term over here and the term over here differs by the constants that's in front of it. Now if both of them are half, we can fill in the hyperbolic cosine, but they're not. Okay, but it's alright, because I can kind of just suggest to you what the shape of this graph will look like. Now we want to bear in mind that C and D are allowed to vary. Okay, so we can't really graph this out because we don't know what C and D are. But let's just ignore the axis for a while for this plane over here. Okay, I want to sketch it out. It will look something like that. Hyperbolic cosine goes like this, right? Hyperbolic cosine. Okay? But actually, since this is a real number, so we'll raise the y-intercept somewhere over here, and the shape would take something like the hyperbolic cosine. So it'll be something like this. Okay, something like this. But as we vary the C and D, okay, we will be able to shift this graph, and the minimum point would also change. So it will look something like that, or something like that, something like that, something like that. Okay, so the shape takes the form of a hyperbolic cosine, but the minimum point changes, okay, depending on whether we change C and D. So have we solved the problem? Well, not yet, because we need to perform some analysis to really somehow fit the graph, or at least say for certain values of C and D, fix the graph so that we're able to, find this missing link. This is still a mystery, the evanescent wave. Okay, so what is the next step? Well, let me just put to you a thought. How about we find the minimum point? Okay, the minimum point of the graph, maybe with that information it can tell us something. Okay, so what's the minimum point? Now, the minimum point, I would want to take the first derivative of this function over here. Your standard differentiation and set to 0. Okay, so which we all do. So let's just say I'll immediately go the first derivative of the magnitude of psi 2 squared, and I'll set that to 0. Now that would give me, this constant immediately disappears. We want to differentiate that with in terms of x, we get nothing. Now when we differentiate these two, this is what we get. Okay, so what we have is that we will have a 2k2, okay, magnitude of c squared and e to the 2k2x. And we'll have a minus 2k2 magnitude of d squared and e to the minus 2kx, okay, and x over here like that. And then now we want to equate this to 0 and solve for x and see what we get. Okay, so let me just remove this. Remember, we are finding a way to find the minimum point. Okay, so let's just set this to 0 so I can bring this over to the other side. And I want to solve for x, right? Okay, so let's just say, so what I have is that the magnitude of c squared e to the 2k2x, I will equal this to magnitude of d squared and e to the minus k2x. Okay, bring this over to the other side, the 2k2 cancels out, so that is great. Now I want to rearrange for x, and it's kind of lovely because now notice that this is e to the minus 2k2x, right? I can multiply by a e to the 2k2x and I'll eliminate this. Okay, so multiplying both sides by that, and then I will bring the c over. What I have is I will have a e to the 4k2x. Okay, I will add the arguments when I multiply, and this equals to the magnitude of d squared divided by the magnitude of c squared. And then finally, I will rewrite this, writing in terms of x. I'll take ln for both sides, so I will ultimately have x is equals to 1 divided by 4k2, and it will be a ln magnitude of d squared divided by magnitude of c squared. Okay, now we are getting somewhere. Okay, now this x value, I want to stress to you again, is the x coordinate of the minimum point for a given c and d. Okay, for a given c and d, which again we don't know. C and d is allowed to vary. But right now we can kind of sketch this out, right? We can sketch it out, which is why in this graph I initially put the magnitude of d squared divided by magnitude of c squared, because now we want to sketch x, okay, as the dependent variable and the magnitude of d squared, magnitude of c squared as the independent variable, okay? And obviously it's a long graph, okay? The constant term we can just leave that one side, and what we have is something like that, okay? And it'll cross at the point when it's 1. Okay, I hope we all can see that. Now, ln 1 is 0, so that's when x is equals to 0. Then as we decrease, we take our ln of a smaller number than 1, and then we basically, x becomes negative, okay, because yes, correct. So when you're taking ln for a number less than 1, x becomes negative, so it goes down like that. Okay, it's a basic ln graph. So what does this tell us? Okay, now this tells us that we have a value of d, we have a value of c. Okay, now I would think that the continuity conditions would allow us to find out these values, or at least, by normalizing conditions we can find these values. And with those values, the ratio between the two gives us the minimum point, okay, of the probability density function psi 2, magnitude of psi 2 squared, the probability density function of psi 2. Now, the y coordinate, I don't know, because the y coordinate I need to substitute back inside. But what I do know, okay, and you have to take my word for it right now, okay, please trust me on this, okay, and I'll bring you to where the information is held. Now, I know that the magnitude of d squared divided by the magnitude of c squared is greater than 1, okay. I know this for a fact. In fact, this is actually equals to e to the 4 k2x, sorry, k2a. Okay, and since a is more than 0, this is actually greater than 1. You just have to take my word for it. Now, actually, if you apply the continuity conditions, which we will do in the next lesson, you will actually get this result. Now, what is important with this result? This result tells us that the minimum point of the probability density of psi 2, okay, so let me just write this down here. The probability density of psi 2, the minimum point of that is going to be a positive x value, okay? Because why? Because now, the magnitude of d squared divided by magnitude of c squared, when 1 is over here, x is equal to 0. But since I know that the magnitude of d squared divided by the magnitude of c squared is greater than 1, I know that the minimum point would exist somewhere in this axis over here. But whatever the value, the ratio between the two, I will get a positive value of x. Can you see that? Okay, a positive value of x. That means what I'll do now is that I would somewhat sketch the lowest point of the probability density of psi 2, something like this, okay? Okay, and I know that it will go this way, okay, because why? Because at this point over here, okay, I can say that magnitude of d squared divided by magnitude of c squared is, it's greater than 1, right? If it's greater than 1, the x value is greater than 1. That's why the minimum point exists in this positive x-axis. But the minimum point I know would somehow have to reach this point over here and join back with the oscillating probability density of psi 3, okay, because of the continuity conditions. Now, why did I sketch it like that? Okay, now this is not exactly right. Now, I hope you take some time to think to match the two graphs together. This tells us the x value of the minimum point of the psi 2, probability density of psi 2. Now, the y value, I don't know. The y value can be something else because I will need to substitute the minimum point x into the probability density which I calculated to get the y value. But that will also depend on c and d, so I don't know. But what I do know is that it would really, the minimum point would somehow be in this region over here, because I know for a fact that the magnitude of d squared divided by magnitude of c squared is greater than 1. So the lowest point will exist in this region over here. And I know that since the wave function needs to be continuous, it will kind of join up as this, from this point to this point over here, okay? That's why the continuity conditions are very important, because the continuity conditions really allows us to really join these 2 points together of the evanescent wave. Okay, that's why they're very important. And since I know that the shape of the graph takes something like the hyperbolic cosine, what I can now draw is that, let's just say the minimum point is over here, because I need to join up with the oscillating solution for x greater than a. It will go in this shape, which I know for a fact because it takes the shape of a hyperbolic cosine, and then it will join up with that point over there. And this completes the picture of what is going on when the energy of the particle is less than the potential V naught. Okay, it's an oscillating solution. When it reaches the potential barrier, the evanescent wave probability density would decay like that, okay, due to all this analysis that we did, and then it'll join back with the oscillating solution when x is greater than a, and continue like that. And this is what we call the tunneling effect, okay, because yes, sometimes the probability density is not physical, but the probability density also tells us whether the particle can exist in that region. The particle exists here, the particle exists here, and due to all these calculations or all this analysis, I know that the motion of the particle or the wave-like behavior of the particle is able to tunnel through the potential barrier and go like this and join up with the solution over here, and it will appear on the other side. Doing all the Fourier transforms, we get a physical solution, but this is what we call as tunneling. Okay? So now the next step is really use the continuity conditions. Everything we said really falls back on the continuity conditions. We do not apply them at all or did the rigorous calculations. That's the next lesson. But what you need to know now is that this is how tunneling works. Okay? The wave function is greater than 0 for x greater than a after the potential barrier. That means that we can find the particle over there. And then, as always, we want to use the transmission coefficients to really see what is the ratio of particles that gets transmitted over. Okay, so tunneling for you, tunneling 101, and the next lesson we're going to go through the rigorous calculations. Thanks.